Barry's talk briefly touched on this, and I'm sure most people in this movie theater would agree that at the very core of all current blockchains is some consensus protocol. At Repi Labs, we're building the first of a new class of permissionless networks for which this is not true. Specifically, what this talk is going to introduce is a new approach to building these types of systems. We're going to move from a protocol-centric view to a state-centric one. The agenda of the talk is, as you can see here. Cool. So with that, we're going to talk shit about consensus. Consensus is obviously super powerful, but with that comes a lot of complexity. There's lots of room for like bugs or inefficiencies. We're going to focus on 3 main points that are really just inherent and pathological about consensus. The first one is you are leader dependent. This is particularly bad if the leader is weak, if they're malfunctioning, or if they're even malicious. You're going to pay the price in terms of latency or throughput or both. Even in the case where the leader is, the median node picked out of the network, we don't have a uniform, the protocol isn't uniform in terms of the nodes. This particular node is distinguished, and the load on the node is much higher than that on the rest of the nodes in the network. If we say that this factor is 2x, then, and I'm just taking that number out of thin air, but assuming that it is, we will reach the network's throughput limit at the point at which the vast majority of nodes are at half their capacity. Not ideal. Third point here is also tied to the utilization of network resources. We can think of the flow of transactions as being, okay, cool, you have the mempool and then you have consensus. So every validator receives a transaction first as, part of the mempool, and then as part of this ordered list that we call a block. So twice. And obviously there's going to be some duplications in both of these, but the point is there's a factor of 2 here, which is suboptimal. Moreover, if we again think of consensus as part of this, 2-part data flow thing, if we just ignore consensus for a little bit and think of scaling out mempools by simply adding workers. In theory, we could do this, right? We could have a bunch of parallel mempools. The validators would simply run multiple workers, and that would lead to, infinite scaling. But with consensus, it doesn't make any sense because you need this very strong, total order relation between all the transactions. So it's like, okay, you've run everything in parallel, but now you need, it's quite literally a bottleneck. All the parallel things now need to be squeezed through to make these humongous blocks. So that approach doesn't make any sense when you need consensus. This talk is going to focus on a framework which is probably new to most people here. It isn't technically new. I think it was introduced in maybe 2015. So Tendermint is actually older, I guess. We can think of BEC as all the honest nodes in the network eventually, they converge toward the same state. So they do not have inconsistent or contradictory states. This is much weaker than Byzantine agreement. The main property that we care about is assume all honest nodes have the same start state. They have the same unordered sets of transactions. Based on this, they can compute the an identical output state. we see that for this, we do not need consensus. We don't need ordering. And returning to this, first of all, you can do this in a completely leaderless way. So you can have, this will essentially be a uniform protocol in terms of the network participants. Symmetric is the wrong word, but you get what I'm saying. So it's leaderless. The utilization in terms of the various participants' network resources is also going to be uniform. And finally here, we can think of a protocol satisfying this if we go back to being like, okay, we have the mempool and then we have consensus on top of the mempool. Well, we have removed consensus, and what we're left with is, we can call it something like a fancy mempool, a mempool with some like gadget on top of it. But the point being, we have fixed this problem of each transaction being delivered twice, like first as part of the mempool, then as part of the block. And then a little bonus here. So now that we don't have consensus, we don't need this strong relation between all the transactions. We can achieve this goal of infinitely scaling the data propagation of the network. Obviously, other bottlenecks will arise, but this approach of scaling out the mempool by having the nodes add workers suddenly works. The main issue here is, of course, and you will have seen this, what can we even do with a system where you don't need ordering in order to achieve state machine replication? What does that even look like? For that, we need this term called invariant confluence. I will get back to this equivalence and what it means, but we need to talk about invariant confluence. The first assumption here, which is exceedingly strong, and we're almost just going to brush it away, is we need commutativity. In a parallel universe, maybe a future talk, this talk would really have been about like CRDTs and commutativity. But many people in this room know what commutativity is, and therefore we will move on to talk about invariance and invariant confluence. In our setting, we view an invariant as some Boolean function on the state space. The example that we will care about is the cryptocurrency one. No one can have a balance less than 0. Now you should read this for 20 seconds, and I'll try to elaborate. The point here is we define validity in terms of the invariant I. So we say that a state S is valid if I of S is true. Assuming some valid state S, assuming sets of transactions T1 and T2, which are arbitrary, and which are such that the state that you get from applying either of those sets of transactions is valid, I confluence is achieved if we can now apply both sets and have a valid state. And I should add, because of commutativity, the order doesn't matter. We can apply T2 first and then T1. Output is the same. We'll see how a very basic example of why this is not automatic. We have this basic system. Alice, Bob, and Charlie have some money. T1 is single transaction. Alice sends 3 monies to Bob. T2, she sends those monies to Charlie. We immediately see that the state that we get from applying either T1 or T2 is valid with respect to I. But we have a problem if we try to apply both. That's not going to work. Alice is going to have balance -1. We're going to try and fix that. The way to fix this is to modify the state model itself, naturally. I mean, we want the state model, the state to satisfy this property. The first thing we do is we add this number that we call a nonce. We need this nonce for commutativity reasons. Transactions look like this, where the additional verification logic that is now implemented is, first of all, we process the transactions in the order defined by the nonces. So this is, a partial order for each account, per spending transaction, if you will. We're also now going to seemingly just trivially solve this issue of iConfluence by saying, applying a transaction that takes anyone's balance below 0 is just going to void it. We're just going to have the same state that we started with. And then, we need the nonces, again, for commutativity. I'm not really going to elaborate on that. But let's see what we get now. So applying this overline T1 to the overline S, as expected, Alice's nonce is now 1 higher. Everything else is as you would expect. But to the point of commutativity, if we here applied T2 first, what we would do in practice is just cache it, and then we apply T1 afterwards. So in practice, that would be like T1 is essentially executed before T2. And what we get now, because we had this rule that we defined, is that the state remains unchanged after applying T2. So we might think that we have achieved iConfluence. Unfortunately, we haven't quite yet. There's a commutativity issue here. I urge everyone to read this paper, which solves the problem from, I'm going to say 2019. It's gone under some radars, I think. Okay. Back to this equivalence. What it basically says is, and we work in the asynchronous or partially synchronous model. Take a system which is defined by a set of invariants. There exists a protocol for this system achieving BEC if and only if the state model satisfies iConfluence for each invariant I that defines the system. We refer to this as the physics of the system. Our approach is about defining data structures, transaction types, and verification logic such that commutativity and invariant confluence are satisfied. There is a clear parallel here to the link between physics and engineering, where you could have the Aristotelian theory of gravity where stone falls down because it just really loves the ground. And the Greeks could still do some things, right? Like they could still invent some engineering stuff. But you are limited, right? Like if you swap out general relativity with that, you're probably not going to get a GPS. So maybe that is actually maybe it's a bit of an exaggerated example because blockchains do work, but we believe that by switching, or rather by using this approach of enabling BEC, which is a strictly weaker framework, where you can get around some of the inherent pathologies of consensus, that is ultimately what's going to lead to the most robust, the most efficient distributed systems of the future. Importantly, it represents a perspective change. And I mentioned this in the beginning. Previously, we've focused on the consensus protocols. We've optimized them as much as we could do. That has been the way to get scalable permissionless networks. We're switching the focus. We're moving from consensus to physics. We're moving from the protocol-centric approach to the state-centric approach. Now, this talk has, hopefully so far, convinced some of us, especially with the added ammo of the linked paper, that we can achieve a consensus-less cryptocurrency. It still remains an open question, though, hopefully for most people here, whether we can do something more interesting with this. How expressive are the systems that we can build using this approach? How interesting are they? Can we do something that's meaningfully different and perhaps better than what currently exists? That's my talk. Thanks.